Thanks a lot for inviting me. So today I will talk about Gaia astrometry and its combination with EP or not EP radial velocities. And to be honest, my presentation will be in two quite distinct parts. The first part will be about Gaia astrometry and its combination with ground-based not EPRVs. And then I will switch to a part on EPRVs and more specifically on modeling stellar activity with Gaussian processes. So all of this enters into a global aim of characterizing the global architecture of planetary systems. And indeed, Gaia astrometry allows to probe the outer parts of planetary systems and giant planets in the outer parts, while EPRVs allow to probe the inner parts on much smaller planets in the inner parts. So combining both methods allows to have a much wider view on the global architecture of planetary systems. So I will start on Gaia astrometry, and I just wanted to show you this small animation of the astrometric motion of a star on the plane of the sky. So basically with astrometry, we are looking at the reflex motion of the star due to the presence of a companion. So it's pretty similar to radial velocities, but it's in the plane of the sky. And in addition to this little wobble due to the presence of a companion, we have the proper motion of the star, which is basically a linear motion in the plane of the sky due to the motion of the star in the galaxy. And in addition to that, we have the parallactic motion, which is due to the fact that we observe from the Earth or from L2 for Gaia. And because we have this 1 year period around the sun, the direction of the star we observe change throughout the year. So we have this yearly signal in the position of the star in the plane of the sky. And of course, if the star is closer to us, this parallactic motion will be bigger, which allows us to measure the distance of the stars from us. So in total, the motion of the star will be the combination of the proper motion, the parallactic motion, and the small wobble, which is due to a planet. So maybe some quick general stuff about Gaia. So it was launched in 2013 at L2, and it started its science operation in 2014. So for the 5 years nominal mission, which ended in 2019. And quite soon, in January 25, it will run out of propellant. So the mission was extended for about 5 additional years, but it will end at the beginning of 25 because of the propellant. So the last data release was in 22. It was GR3. And it was only based on the first 34 months of data, so about half of the nominal mission. And the next release, DR4, will probably be at the beginning of 26, and it will be the first release with astrometric time series available for the community, and based on the 5-year nominal mission. And then there will be a DR5 later. We cannot tell when exactly from now, but it will be on the full 10 years or so of the extended mission. So quickly, the design of the instrument of the spacecraft. So Gaia has two field of views, two primary mirrors that are looking at two directions in the skies. And it's scanning, so it's rotating with a 6-hour rotation period. And the spin axis is precessing with a 63 days period. So this is typically the period that will enter in the scanning law of the satellites. And then Gaia so scanned the whole sky for years now. So the main difficulty of this mission is that it needs to define its own reference frame. It needs to define its own catalog of targets and to find the motion of each star individually all at the same time. So it's a huge machinery to observe 1 billion stars and be able to constrain the motion of the spacecraft and the motion of each star in the sky. So there is a huge consortium to deal with those data, the DPAC, the Data Processing and Analysis Consortium. And a very important, so it's a lot of working groups. A very important working group is CU3, which is doing this reduction, going from the raw data on the CCD to extract the photometry, the astrometry of the targets. And it's a huge work, as I said, to deal with all the possible effects in the instruments. And then, so in Geneva, our team is involved in the non-single stars working group, and more specifically in the planets subgroup, which is a collaboration between Torino with the team of Alessandro Sozzetti and our team in Geneva, led by Damien Ségantin. So we did have some release of planets in DR3, but it was for us mainly a training exercise, DR3, because initially it was actually not supposed to be a planet release at all. It was supposed to be the first non-single star release, but mainly with binary stars. And because it's only based on 34 months of data, it was quite challenging to have some planet detection. And also because it was still affected by quite a few systematics in the reduction of the astrometry. So we had some huge effects, especially for red targets, with a systematics that could mimic the presence of companion. And we also found a bug in some coordinates conversion later after the release, which introduced some false positives. So it was quite challenging to process those data for DR3. But we still managed to have some interesting results out of it. So here I illustrate the case of HG 81040, which is one of the planets that we found with DR3. So it was part of the release, and it was also highlighted as an image of the week on the Gaia website. So you have some more information about it on the Gaia website. And what you can see here is the astrometric orbit of this target. So it's about 800 days, the orbit. And it was obtained only with Gaia astrometry alone. And we could confirm it because it was actually known from radial velocities, so from a paper by Alessandro Sozzetti in 2006. And when we overplot the radial velocity curve that we expect from the astrometric solution with the radial velocity measurements from the paper, we see that it's overlapping quite well. It's agreeing quite well, which confirms that the processing of the data with Gaia is correct. And so the mass we obtained for this target for the companion is about 8 Jupiter mass. So already with GR3, we were able to detect some low mass companions with Gaia astrometry. So as I said, for now, the astrometric time series are not available for the community, but people came up with some nice ideas to still try and combine Gaia astrometric data with radial velocities. So the first technique, actually the two first techniques here were already possible with previous release from Gaia. So the idea for the first one is to combine EPRCOS measurements and Gaia measurements. So the two are astrometric mission. EPRCOS was launched in 1990, around there. And it's, of course, much less accurate than Gaia, but because of the time between EPRCOS measurement and Gaia, we can determine an average proper motion between EPRCOS and Gaia and compare it with the instantaneous proper motion that is derived by Gaia. And if the two agree well, then it means that there is a single star. But if you have a companion around the star, you might have some anomaly in this proper motion, which can be used to constrain the inclination and the longitude of the node of the companion, and thus the true mass of the companion. Similar approach is to look at Gaia excess. So again, it's looking at a single star solution in Gaia, but looking at basically the jitter that is found by Gaia. So if you have a companion, it will introduce some jitter in the residuals of the single star solution. And by looking at this, it can provide constraints again on the parameters of a companion that is already known from radial velocities. I have to say that this second method is a bit dangerous because with Gaia GR3, we still had lots of systematics. And so it means that the excess noise that is found by Gaia could be due to the companion, but it could also be due to some systematics. So it must be applied with care. And the last method, which was made available because of DR3, because in DR3 we provided some non-single star solutions, so some two-body solutions. So the idea was to take the Gaia astrometric solution as a prior for radial velocity fit in order to further constrain the orbits. And it was applied to a few targets. For now, we are focusing on DR4. So it's still a work in progress. It will be released around beginning of 26. And as I said, it will be the first release with astrometric time series, so the community will be able to play with the astrometric time series with this release. The reduction of the data has improved a lot since DR3. A lot of systematics were identified and correctly modeled to have much better astrometric time series. So we just obtained the latest reduction of DR4. So the people that are working on the reduction of the data now stopped working on DR4. They released their reduction for DR4, and they are now focusing on DR5. So we just obtained it, so we didn't have time to look at the latest reduction of the data, but based on what we had earlier, we typically see RMS of the order of 50 microarcseconds. That is to be confirmed, but to give you an idea, Jupiter mass planets at 1 AU around the solar mass star at 10 parsec from us would yield a signature of 100 microarcseconds. So that would be, of course, challenging to detect, but this gives you basically an idea of the order of magnitude of what we should be able to achieve. And the best performances will be in the range 1 to 10 years, because we'll have 5 years of data with DR4. So another trailer about DR4, maybe you've seen it lately in the news. So with the preliminary data from DR4, we were able to detect black hole 3, Gaia black hole 3, which is, so of course, the third black hole detected by Gaia, but it has the particularity to be quite massive. So here you see the orbit of the stellar companion to this black hole. So of course we cannot see the black hole itself, but because it's in a binary, it's a binary with a star, we observe the motion of star, which is of course much larger than what it would be for a planetary companion, because here we have a huge astrometric orbit due to the black hole, because it's much more massive than the star. So it's actually quite easy to detect those black holes compared to tiny planets. And you see also the radial velocity curve due to this black hole. So Gaia also has some radial velocity measurements on board, and you see the orbit, the radial velocity curve. So here the units are kilometers per second, and the peak to peak it's about 100 kilometers per second. So with the precision of Gaia radial velocity, about kilometer per second precision, we are able to very easily detect it. So we actually don't need EPRVs to do great science. So as I said, one particularity of this black hole is that it's a 33 solar mass black hole, and it's actually the most massive black holes that we detected in the galaxy. So of course, with gravitational waves, we were able to detect more massive black holes, but it's all outside our galaxy. And all the black holes that are known in the galaxy are represented here. So it's quite a new parameter space for our galaxy, this black hole. So here it's the black hole 3 compared to the masses of black holes obtained from gravitational waves. And you see that, so the red curves is the mass distribution of black holes from gravitational waves. And you see that it's double peak, so there's 2 modes, and that black hole 3 lies exactly in the middle of this peak around 33 solar mass. So of course it's very small number statistics, but it's interesting to see that it lies in this peak. So the data are publicly available with this publication of PH3. So the astrometry and radial velocity from Gaia are available, and there is also a Jupyter notebook, which is available to play with those data easily. So to come back to the planets with Gaia, so in the pipeline, and more generally when dealing with Gaia astrometry, we need some quite efficient method to be able to apply it to many targets. Of course, approaches like nested sampling are very interesting to apply for specific targets, but to apply on all the Gaia sources, it would be way too expensive. So we came up with a much simpler approach based on periodograms and local maximum likelihood fits. So we propose an approach with a periodogram and an analytical false alarm probability estimate. And overall, this periodogram, false alarm probability, and maximum likelihood fit takes in average about 1 second per source. So it was implemented in the official Gaia pipeline as part of the pipeline. And we also provide a Python package with open source code. So the approach is to have a general linear periodogram, which can take into account the proper motion, the instrument offset, etc. And to compute a power based on the chi-square ratio. And then to have analytical estimates, which are based on the method proposed by Baluev in 2008. And it was mostly focused on radial velocities, this method, but it's actually very general, and it can be applied both to the radial velocity, of course, but also to astrometry alone, and also to the combination of astrometry and radial velocities. So this is this application to astrometry alone and the combined astrometry and radial velocity that we proposed in the paper in 2022. And then once we have detected a significant periodicity in the data, our method consists in trying to obtain an initial guess of all the orbital parameters, basically based on the periodogram. So by looking at the amplitude and phase that we have at the period of the candidate and at half the period, we are able to obtain estimates, analytical estimates of the eccentricity, the argument of periastron, etc., etc. This method was applied to the radial velocity case, but we also extended it to the astrometric case and to the combination of astrometry and radial velocity. And it's allowing to obtain very good initial guess for local minimization, which can then be much more efficient because we start from close from the solution. So here I show some example based on EPRVs data, because of course Gaia astrometric time series are not publicly available, so I cannot use them. So here it's a binary star with EPRVs astrometry and chorally radial velocities. So in this case, we see the companion both in astrometry and radial velocities, but by combining both time series, we have a much more significant detection. And we can, of course, then by fitting both, obtain the inclination, the true mass of the companion and the longitude of the node. A second example here is a case where we cannot detect the companion in astrometry alone. In radial velocity, we detected the false alarm probability is very large, so it's not very significant, but it's actually a huge signal. It's just that the sampling is not great, so the periodogram approach is not perfect in this case. What is interesting is that you kind of see a peak in the astrometry at the correct period, but it's not the highest peak because it's low signal to noise. And then when you do the joint periodogram, the period is significant at the correct period. And you actually are able to constrain the astrometric orbit, knowing the period from the radial velocity, and doing the combined fit allows to constrain the inclination again of the binary. So all of this is applied to EPRVs, but of course onto binary with EPRVs, but with Gaia, we will be able to do the same for planets. Yeah, a quick note on the eccentricity in radial velocity and in astrometry. It's an interesting difference between radial velocity and astrometry. So you are probably aware that in radial velocities, when you have a very eccentric signal, a very eccentric companion, the periodogram approach starts to fail because actually the amplitude of your peak in the periodogram decreases with eccentricity, and you spread the energy in all the harmonics of the period of the planet. So here you can see on this plot the fraction of the power that is in the fundamental, in the period of the planet, and you see that it decreases a lot with eccentricity. And in blue, it's the first harmonic. So you see that at high eccentricity, the periodogram approach is not a good one for radial velocities. But actually, for astrometry, the behavior is not the same at all. You see the red curve here that even at very high eccentricities, the power fraction in the fundamental is still above 80%, which means that even at high eccentricity, you should be able to detect the companion with the periodogram approach. So it's an advantage for astrometry compared to radial velocity, but a drawback of this, it also means that it will be difficult to measure precisely the eccentricity based on astrometry. For given signal-to-noise ratio, the precision you will get on eccentricity will be much smaller with astrometry, because the signal depends a lot less on eccentricities than for radial velocities. So to summarize, by combining Gaia astrometry on ground-based radial velocities, so of course you will be able to have much better constraints on better detection capabilities for companions. If you consider a Gaia detection, using additional radial velocities can, of course, help to confirm the detection if it's dubious, but more importantly, it will help to better constrain some parameters on, for instance, the eccentricity. But basically, you don't really need radial velocities if you have a strong detection with astrometry, because it constrains all the parameters. For radial velocity detections, having astrometry data in addition to it allows to constrain the inclination and thus the true mass of the companion and the longitude of the nodes. And if you have multiplanetary systems, it's even more interesting because you will be able to constrain the mutual inclination between the different companions. Okay, so here is the tentative transition slide. So as I said, basically all of this for me enters into the idea of constraining the global architecture of planetary system. And if we want to be able to study the coupling between outer giant planets and inner smaller planets, observing the same system with Gaia astrometry and EPRV allows to study this kind of coupling. So I will switch to the second topic, which is focused on EPRVs and more specifically on modeling stellar activity with Gaussian processes. So typically the motivation is using Gaussian process to model stellar activity is widely spread in the community. And basically the motivation to do this is because we typically know the mechanisms that are responsible for the signal that is present in radial velocities. Typically the granulation, oscillations, spots and faculae, the rotation of the star, and magnetic cycles on longer timescales. So we kind of know what are the typical mechanisms on their timescales, but it's difficult to have a direct model of it, and it would be completely degenerated to try to model all of those effects to constrain to fit the radial velocities. So this is a typical situation where Gaussian processes are used. So typically, the hypothesis that is made is that our radial velocity time series is the sum of some deterministic part in which we are mostly interested, the planets, etc., and the activity, which is modeled through a Gaussian process, and of course, measurement error. So this Gaussian process is not known, but is assumed to follow a Gaussian distribution with some covariance. And this covariance that is crucial to model the activity. So it is often assumed to be stationary, which means that this covariance only depends on the lag between two measurements. And then the measurement error is also often assumed to be Gaussian, which means that in total, the likelihood of our model is Gaussian, with the covariance being the sum of the two covariants from the Gaussian process and from the measurement errors. So one issue with Gaussian processes is that it's very flexible. And also the radial velocity signatures of planets and stellar activity are quite similar, especially the activity modulated by the rotation period of the star can mimic planets, so that's why we want to correct from it. But it's also an issue because Gaussian process, if they are able to model this activity modulated by the rotation period of the star, they are also able to model the signature of a planet. So actually, planets can be absorbed by a GP. And they are quite efficient in modeling the signal due to a planet. So an approach that has been proposed by the work of Suzanne Aigrin in 2012 and Raj Paul later in 2015, is to model this activity on the radial velocity at the same time as on activity indicators. So to model with the same GP the time series of the radial velocities and of activity indicator in order to constrain the GP with the indicators to prevent a bit this overfitting of the GP and to prevent the GP from absorbing the planets. So typically, the model looks like this. So the activity-induced radial velocity is supposed to be a linear combination of a GP and its derivative. And the same for the bisector and the air prime HK. But more generally, you can have any number of indicators, and you will have some deterministic parts, so the offsets, planets, etc., for the radial velocity, and a linear combination of the Gaussian process and its derivative for each time series with different amplitude in each time series. And then you need to model the covariance between all the measurements, so all the time series at all times. And to do that, you need to compute the covariance of your Gaussian process with itself, with its derivative, and between the derivative at two different times. So this is to model all the time series at the same time with the Gaussian process. So here is an example on HD 13808, where you see the radial velocity curve here. So here it's the full time series, and here a zoom on a specific part. The bisector on the R prime HK. And you see the model with the Gaussian process here in red and its derivative. And you have a linear combination of the two for each time series. So this allows to model the radial velocity with a Gaussian process, but to constrain the Gaussian process with activity indicators. The problem with this approach is that the cost of computing the likelihood for a Gaussian process typically scales as the number of measurements cubed, sorry. So this cost grows rapidly when the number of measurements increase. So typically, when you have more than 1,000 measurements, it starts to be quite heavy to do those computations. So that's why people came with a clever method to compute the likelihood and to have Gaussian processes that are much more efficient than that. So if you look at this likelihood here, so Gaussian likelihood, of course, if your covariance matrix C here is diagonal, then everything simplifies a lot, and the cost is linear, because you don't have anymore, if C is diagonal, the inversion is very easy, computing the determinant is very easy. So with a diagonal matrix, it simplifies a lot. But more generally, if you have a sparse representation of the covariance matrix and some dedicated algorithms, you can reduce the cost. And that's the idea behind celerity from Maki et al. 17. So the idea in celerity is to use semi-separable matrices. And the main trick behind that is to notice that if you have an exponential decay kernel like that, so just the correlation between two measurements at two different times is the exponential of the lag, you can split this exponential in the exponential of minus lambda ti times the exponential of lambda tj, assuming that ti is greater than tj. And by splitting this kernel in a product of two components, one depending only on I and the other depending only on j, you can actually describe the full covariance matrix with only three vectors: the vector u with the negative exponential, the vector v with the positive exponential, and the diagonal part of the covariance matrix. And basically, your covariance matrix is, of course, n by n matrix, but you can represent it with only those three vectors. So, and then you use this representation. You never compute the full covariance matrix, but you use this representation to do all the computations. So the matrix inversion, the determinant, etc. You never actually compute the full covariance matrix, but using this representation, you can do all the likelihood computation. And actually, the covariance you can represent with this method is more general than just the exponential. You can have any combination of exponential and cos and sine terms. And you can add those terms. So the cost in the end of computing the likelihood will typically scale as the number of terms squared times the number of measurements. So if R, the number of terms in your decomposition here, is reasonable, is much smaller than the number of measurements, you will reduce the cost by a lot. So now, celerity was mainly used for photometry, but for radial velocity, the issue is that we need to apply it both to the radial velocity and to activity indicator. So we need to model several time series with the same GP. And we want to be able to model it with the Gaussian process and its derivatives. So those two technical problems have actually been solved now. So the first one with Gordon et al. 2020, to be able to model several time series at the same time with a celerity GP. And more recently, we did the case of a combination of the GP and its derivative in the same framework. So I will not enter into the details of those work, but basically the idea is to define a merge time series with all the measurements from all the radial velocity, the activity indicator. You put them all in the same vector, sorted by increasing time. And you can somehow apply the celerity method to this merge time series. And so again, I will not enter to the detail, but with the derivative, it's actually pretty similar. You combine everything to be able to use the celerity method on the full time series, the merged time series. And what is quite astonishing, I found, is that introducing the derivatives of the GP in the model actually doesn't increase the rank, so the number of terms we need in the celerity kernel. So it comes from free to add the derivatives in the model. So all of those methods are implemented in a open source package called Spliff, which is available on pip and Conda. So those very efficient methods, they have one drawback. It's that you cannot use any kernel you want. You need your kernel to be semi-separable. So basically, the Mattern family of kernel are semi-separable, so you can use them. The exponential, the sinusoidal kernels also, and any combination of those kernels. But for instance, the squared exponential, so the Gaussian kernel, or the squared exponential periodic kernel, which is this one here, which is often used in radial velocity analysis. It's not semi-separable, so you cannot use this kernel right away. But you can actually try to mimic those kernels that are not semi-separable with a combination of semi-separable kernels. So you can play with different combination of semi-separable kernels to try to be as close as possible to a kernel that you want to model. So here I played this game for the squared exponential periodic kernel, which is the one that is often used for radial velocities. And you can quite well represent, approximate it with a semi-separable kernel. So of course, if you add lots of terms in your semi-separable decomposition, then you increase the cost of the evaluation, but still it can be much more efficient than dealing with the full covariance matrix. So here I put some comparison of the costs of the usual full covariance matrix method and the method with semi-separable kernels. So of course, for large number of measurements, it's pretty interesting to use those methods. If I still have time, I don't know if I still have time.
Yeah, if you could wrap up in the next like 3 to 4 minutes, that'll give us a bit for questions at the end.
Okay, so in the last part of the talk, I wanted to present a work that we are doing with Nathan Hara to try to put a bit more physics into those Gaussian process methods. And basically, the thing is that, for instance, with the squared exponential periodic kernel, so the one that I shown earlier, basically, apart from the periodicity, so you have one of the parameters is the periodicity of your Gaussian process and typical decay time scale of the kernel. It's difficult to interpret the parameters of those Gaussian process, and they are not really physically motivated. So our idea was to try to put a bit more physics into the kernel we use, based on our knowledge about the processes, so granulation, spots, faculae, etc. So typically, we know we now have a lot of detailed physical models of at least the sun and the stellar activity on the sun, with different processes that happen on different timescales. So the granulation, supergranulation on minutes to days, the spots and faculae on timescales of the day or months. And then on longer timescales, you have the magnetic cycle. So all those processes, we quite know them well for the sun, at least. And the idea is can we take some of this knowledge to put in the likelihood of our model? So basically, if we assume that our likelihood is Gaussian, it means putting this knowledge into the mean and covariance matrix of our likelihood. So we are working on this Fenrir model. So the idea is to consider first a single spot or a single facula and with some parameters, and to describe its effects alone. So for instance, if you have a dark spot on the star, due to the rotation, you will see first on the radial velocity, you will see some basically Rossiter-McLaughlin effect with an increase of radial velocity first and the decrease. But you also have some inhibition of the convective blue shift. So you have different effects that you can describe for a given spot or a given feature. And then in total, on the sun, you have some rate of appearance of those features. So typically, the rate of appearance of spots on the sun, which you need to model. And for each spot that appear, you have some parameters that you need to draw. So it's this last part of the model where you need to describe as a function of time the properties of the spots, etc. So taking all those components of the model, we try and compute the covariance matrix of the measurement, so of the photometry, of the flux on the radial velocity at different times. And basically, you need to integrate over all the spots that appear on the star with their properties. So gamma here is the properties of the spots. And G and H are the effect in flux on the radial velocity. So taking all those components, you can compute the covariance matrix you expect between two measurements of the sun or of a star. And so typically for a spot, our assumption is that we have some window function that models the spots appearing and disappearing times a periodic part, which is modulated by the stellar rotation. And if we assume that so the spot appears at a random longitude on the sun, we can actually then compute the covariance matrix between the measurements and model it with a celerity kind of kernel. So we can do the computation very efficiently. So with this assumption. And basically, so knowing the effect of a spot in flux and in radial velocity based on the model we have, we can determine analytically this decomposition in the periodic part here. So we can compute everything analytically and compute the covariance matrix analytically in a very efficient manner, assuming a given model for the spots and faculae. And we can also, in this representation, let the effect of a spot, this periodic part of the spot completely free. So it's a Fourier decomposition. We can let the amplitude here, alpha and beta, completely free. And this will be, of course, much less physically motivated because we don't put the knowledge we have on the physics, on the effect of spots, that it allows to have a new family of kernel which is efficient to compute with celerity. So this model, both the physics-based model and the data-driven model, are also available with the Spliff package. And so we tried to apply it on the sun data. So we took the ARPS-North time series that are available from the paper of Xavier Yumusk in 2020. So it's data from 2015 to 2018, together with some photometric data from source on a larger time span, so between 2003 and 2020. Here you are just a zoom of this data. And so we modeled it with our physics-based model. And you see here the parameters that we obtain with this. So typically the parameter we let free is the rotation period, the inclination of the sun, the position in latitude of the spots. So we have a distribution of spots and an independent distribution of faculae. So we have two populations of features, the spots, the dark spots and the bright faculae. So we let all those parameters free, and what we obtain is that we constrain quite well the inclination of the sun. So because we observe from the Earth, the apparent inclination of the sun varies between -7 and +7 degrees. And here we are able to constrain it to be close to 0 degrees, basically about 2 degrees, which does make sense considering that it's oscillating around 0. And we are able to see that the spots are typically close to the equator. Typically, I think that they are around 15 degrees with a scatter of 8 degrees. So we typically reproduce well what is observed on the sun. And here you can see the covariance. So basically the kernel, so here the kernel for radial velocity with itself, for the photometry with itself, and the cross correlation between the two time series that is modeled with our kernel. We also did some cross-validation tests. So we took out part of the data, of the radial velocity data. We took chunks of 30 days, several chunks of 30 days out of the data set. And we compared different approaches. So the physical model that I described here, the data-driven approach, where we let the Fourier decomposition completely free, and the more classical latent GP with an approximation of the squared exponential periodic kernel, and so this GP with its derivative. And we find that so the best kernel we obtain is a data-driven kernel, a Fernrehr data-driven kernel. But the second one is our physical model. Well, basically, it might mean that we still miss some physical mechanism in the physical model to be able to be as precise as the data-driven model, but it's quite encouraging to have those results. So with that, I'll end the presentation and take some questions if there is still time.
That was wonderful. Thank you so much. I invite everybody to do the little clapping hands emojis for a truly excellent talk. If there are any questions in the audience, I know we're a few minutes over the hour, but please feel free. Nathan, I see your hand. Go right ahead. Oh.
No, sorry, that was a mistake.
Trying to clap. Okay, questions from the audience? Eric, go right ahead.
I can get us started. So if I have the squared exponential kernel, the Gaussian process is infinitely differentiable. And if I have a Matern kernel, I can specify how many times differentiable is based on the order. If I have an exponential kernel, my understanding is the Gaussian processes themselves are not differentiable. And yet we're using the derivative of that Gaussian process in these models. So I'm trying to understand, how are you dealing with the non-differentiability of the current of the GPs coming from a exponential kernel?
So for the part with the GP and its derivatives, you mean?
Yeah, you had you're using an exponential, absolute value kernel, yes. And
yeah,
I believe those GPs themselves are not differentiable everywhere with respect to time, and yet you're using that, I think, as a latent process and its derivatives. So I'm wondering if there's some averaging or something so as to get around that happening.
No, so first, for the last part of the talk with the Fenrir model, we don't have the derivatives. So we don't need the GP to be differentiable. Right. And actually, for spots that appear, that are modulated by the rotation period, it's not that obvious that the signal would be differentiable, because when the spot disappear and appear because of the rotation, you have some windowing effect that might introduce some non-derivability, non-differentiability. But for the case of the GP with its derivatives, actually, we do not use the exponential kernel itself directly, because you can actually use some Matern kernel. It's also you can also model Matern kernel with celerity with the celerity method. And those Matern kernel, the Matern 3.2 is it's once differentiable, the GP with Matern 3.2, and the Matern 5.2 is twice differentiable. And
okay, so you were working with the Matern kernels, not the exponential kernel, when you're doing the latent process.
Yes.
Okay, that explains it all then. Thanks.
Yeah. Yeah. Otherwise, it doesn't work. You cannot actually compute the covariance matrix itself if you rely on a non-differentiable GP.
Okay. Other questions from the audience? Feel free to raise your hand or unmute. Well, folks ponder for a moment, I'll ask. So you mentioned towards the end that right now the data-driven models are still performing a bit better than these physically motivated models, and that there might be some bits of stellar or heliophysics that you're missing here. Have you guys thought a bit about whether there are, classes of phenomena that are not well captured yet, or whether, what directions you could try and look in next to identify what else to include in the physically motivated models?
Well, to be honest, it's quite recent results, because up to recently, we were having even worse results because we were actually trying to model the spots and faculae as a same population, basically assuming that the spots and faculae appear at the same location on the sun, because we often see when you have a spot, we often see surrounding the spots a bright region. So we were making the approximation that spots and faculae appear at the same location at the same time. And trying to model the average effect of such a region with a spot on the facula. And when we were doing this, actually, you have the result here. It's the mix latitude distribution here. We found an inclination for the sun of 30 degrees, which is not quite the correct answer. And we, basically switching to two different populations for the spots and faculae, and considering they are completely independent, gives much more reasonable results for the inclination for the latitude of the spots and faculae. So now, additional property that we do not model. Well, basically, we assume the latitude distribution of the spots to be constant throughout the time series. And we actually know that, well, we can see it actually on this plot here. As a function of time and as a function of the magnetic cycle, the location of spots tend to go from higher latitudes to the equator. So maybe some effects like that could introduce, well, could not be well modeled by your framework.
Yeah, makes sense. Thank you. Eric, I see your hand back up.
Going back to the table you showed, the last row was interesting to me because it looked like there was a model that got the inclination right, had a very low training RMS, but did significantly worse than the test set and the cross-validation. Could you tell us more about what that model is and what didn't work?
The last one?
Yep.
So okay, so so for the physical based model, we have so those two hypotheses. So either to have two separate populations for the spots and faculae, or a mix of the mixed effects. And we also have either a distribution of latitude of spots. So we consider a symmetric distribution in both hemispheres, and with an average latitude with some scatter around it. So this is the lat distribution models. And the up lat is assuming just a discrete latitude for the spots. So actually two discrete latitudes, one on the northern hemisphere and one in the south hemisphere, but with just a single latitude of spots. So it's a simpler model where we don't have a distribution of latitude, but just a fixed latitude. So yeah, it's a bit surprising that the inclination is that different between those two models, because the distribution of spots is quite restricted anyway. But yeah, maybe the fact that you still have some scatter in the distribution of spots makes some difference between the two models.
And can you clarify again the difference between the mixed and separate?
So the separate is basically we have two GPs, one modeling the spots and one modeling the faculae, and they don't
okay.
to each other, except we share the rotation period and the inclination.
Okay.
But that's it. And the mix one is basically trying to model the effect of a region with some spots and bright area surrounding it. So we take the average effects of the two.
And so is there something like a lifetime distribution that differs between the spots and the faculae when you have separate
Sorry?
distributions?
Can
Is there something like a different lifetime distribution that the two spots and faculae get in the separate model?
I didn't get the
You said that some parameters were shared, but some were different. And so I guess I'm wondering, what are the parameters that are allowed to be different? Is it a lifetime distribution, or, I mean, you mentioned the latitude distribution, but are there other parameters that are also different between the two of them?
So here you have all the parameters for so here it's a separated model. So the rotation period and the inclination are the same for spots and the faculae, but then the latitude of the spots and the faculae are fitted separately, and the amplitude of the radial velocity photometric effect of the Rossiter-McLaughlin effect and the convective blue shift effects are fitted separately. Also for the pure photometric effect in the photometric time series, and also the time scales of disappearing of the spots on the faculae. So, for instance, here you can see that the time scales for the spots is fitted to 40 days, while the time scale of disappearing for the faculae, it's about twice, it's 73.
Got it, thanks.
So I think that's kind of what is observed on the Sun, that the faculae typically disappear more slowly than the spots. So it does make sense maybe that fitting them separately give better results.
Okay, why don't we wrap it up there, because we're a fair bit over at the top of the hour. But thank you so much, Jean-Baptiste, for sticking around and answering a bunch of questions. And thank you again for a fantastic talk. As always, it's being recorded. We'll post it to the RCN Google Drive tomorrow or Monday. Thank you all for calling in. I hope to see many of you at our machine learning workshop early next month, and at one of the many conferences that I mentioned earlier in the presentation. So thanks, everybody. Have a great rest of your Thursday, and I will catch you in June. Bye.